Me? If you can't hear me, raise your hand. Ha 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 ha. That joke never gets old. Okay, let's get started. Okay, so the title of this talk is The 4 Rules of Simple Design, some lessons from watching 1,000 programmers work on Conway's Game of Life. It's actually more than 1,000, but I didn't feel like actually counting it. About me, I'm a developer. That's my cat, Zach. She's awesome. So I want to start by talking a little bit about Code Retreat. Code Retreat, which is where a lot of these lessons came from. I've been facilitating it. It's a day-long workshop. We work on Conway's Game of Life. Basically, we do 45-minute sessions where we work on the problem, and then after every 45 sessions, we delete all the code. And then you start again. And then each session, we introduce new constraints like no if statements or cross method boundaries, different things that let you practice. And then we swap pairs after every session. It's focused very much on low-level development skills. The goal isn't to finish the problem, but to practice trying out new techniques. We do TDD, iterative design, we pair, and we really focus on these 4 rules of simple design, which over the years I've started to come to accept as the core design principles for writing code and when you're doing refactoring. All the other principles tend to come from them. I've found that you can usually, just by following these rules, you can build up all the rest of the design principles, such as solid, etc. The original idea for Code Retreat happened in 2009. 4 of us, Patrick Welsh, Nayan Hajratwala, Gary Bernhardt, and me, we were at a conference complaining and bemoaning about the state of everybody else's code, which is a common practice for developers to do. From 2009 to about 2013, I ran these code retreats around the world, spreading it, meeting other people, having other people facilitate, and just sort of doing it. So every time I ran a code retreat, I would see usually about 20 to 30 people work on this problem in pairs. And since we swapped pairs, every day I saw about, whatever 20 times 5 is. Early on in the years of Code Retreat, the format was heavily influenced. Alex Balbuaca from Romania, J.B. Rainsberger, some other people had some really big impact on how the format itself evolved. We started this thing called Global Day of Code Retreat. It's a global event where we have code retreats running in cities all over the world. 2011, we had more than 100 cities take part, all on the same day. 2012, we had 150 plus cities. And then last year, we had our biggest yet, which we had 179 cities all doing the same workshop on the same day. So there's a lot of learnings from watching a lot of different people try the problem. And so this talk is really about sharing some of the design ideas that I've come up with, or not come up with, but realized after watching people try to work on this problem. It turns out that most developers there's about 3 or 4 or 5 different approaches people take. And so seeing it over and over again, I started to get an idea of some of the reasoning behind why they do that, as well as how to apply the 4 rules of simple design to improve the code. So this talk, I'm going to share some design lessons, just a little bit more talking, and then I'm going to open up Vim, and I'm going to start writing some code and showing you these examples. It's really about subtle design decisions. Some of the things that I'm going to be showing seem focused on minutia, and that's really what they are. They're not just these gross, don't write 100-line methods. They're really about very subtle understandings of design, aiming for the goal of being able to change your code more rapidly. Since the only thing that's constant in software development, the only thing that we actually know 100% for sure is that your design or your requirements are going to change. As you build your software, you're going to have to make changes to it. So a good design probably doesn't exist, but a better design, if you have a choice between 2 of them, a better design is one that's more easily changed. So this talk's really about just a couple design decisions that I've seen over the years that make code easier to change. 4 rules of simple design were originally codified in the late 90s by Kent Beck and have sort of been discussed and everything, but they haven't really changed that much. The first rule is that tests pass. This contributes to your design because if you can't prove that your system works, it doesn't matter what kind of design you have. You've got to be able to prove that it works. The second is that your design and your code expresses the intent. It's clear, it's concise, you can look at the code and understand what it's supposed to be doing. This often I think of as just good names. Name your stuff well, spend the appropriate time, give it the respect it deserves about naming things well. And if you do that, you start seeing influences on your code. The third is no duplication, or the DRY principle. I don't know if anybody's heard of that out there. It's the don't repeat yourself principle. Too often we think about duplication in terms of code, but it really states that all knowledge in your system should have one and only one representation. And we'll have an example in here of knowledge duplication rather than simply code duplication. And the fourth is small. Once you've accomplished these other 3, look to see if there are too many pieces in your system and get rid of things that you don't need. This is sort of the least of them, the last rule that you apply. In general, 2 and 3, the expresses intent and the no duplication, you iterate between. You fix names, that exposes duplication. You fix duplication, that exposes naming problems. And you sit and refactor. And for me, when I'm actually sitting there writing code on a day-to-day basis and on a minute-to-minute basis, when I'm making my refactoring decisions, these are what I'm keeping in mind now, not larger scale, higher level design guidelines. I already talked about that. Conway's Game of Life, which is what we work on at Code Retreat, it's a very simple thing to work on. It's simple to understand, but the beauty of it is that with these very simple rules, you can get some amazingly complex patterns. I have a couple examples here that, unfortunately, so basically, in Conway's Game of Life, you have a grid, an infinite grid in 2 dimensions, where each cell, in here it's the white and the black, each cell has 8 neighbors, the diagonals count, and a cell is generally considered alive or dead. And the point of the problem is to lay out an initial pattern, such as these, and then to iterate generations, to apply some simple rules and figure out what the next iteration looks like. And we'll go over what the rules are. There's 4 rules. But basically, you can get movement. You can get some very complex structures. So, for example, this is one that is just sitting there iterating, running the rules over and over again, building generation after generation. Here's another complex pattern. You can see that there's lots of subtle patterns and structures inside when you apply these rules. So, oops, let's bring this back up. Infinite 2-dimensional grid. Again, cells in the grid are considered alive or dead. You set up an initial pattern, and then you calculate subsequent generations based on simple rules. The rules themselves are if a cell is alive, you count the number of living neighbors that it has, and it stays alive if you have 3 or 4 living neighbors. It dies if you have less than 3. It's sort of an underpopulated, undernourished, a lonely environment. If you have more than 4 living neighbors, you also die in the next generation. And this is sort of an overpopulation situation. Dead cells, if you have a cell that is dead in one generation, and it has exactly 3 living neighbors, it comes to life in the next generation. So just by applying these rules over and over and over again, you can calculate subsequent generations, and you get those really complex patterns. I already showed those. All right, let's look at some code. So, as I said, I'm just going to show some general things that I've seen with some small coding snippets and then doing some analysis on that code based on the 4 rules of simple design and refactor it into something that generally is easier to change. Now, it will seem a lot like I'm nitpicking, like I'm looking at very small things that in a larger code base or on your day-to-day, you may go, oh, I don't even worry about that. But these are really important, and if you get them into your mind, you can see and get a lot of benefit out of there. So the first one I want to talk about is, I'm actually going to just type stuff in now, is in general, the first time that people build this, they look at it and they say, well, I have a cell. There's this concept of a cell. I'm going to do my examples in Ruby, but I'm going to trust that people can read Ruby. It's not really complicated. I'm not doing anything crazy. So in your head, translate over to some other language if you're in another one. So in general, people build a cell class. They start with it. Often we've been brought up with a design methodology where you look at your statement of the problem, statement of the domain, and you find the nouns. And you say, well, there's a cell in there, clearly. And so they'll generally come up and build to attribute or an attribute called alive. And this is usually either true or false, so it's a Boolean. Thinking that's what the problem statement is. You have a living and dead cells. Then, since we have to calculate what the next generation looks like, we'll generally write something like this. Have a method that looks at it in the next generation, and you'll say something like, well, if I'm alive, then let me look at the number of neighbors, if it's equal to 2, or if the number of neighbors is equal to 3, then I stay alive. Otherwise, if number of neighbors equals 3, then I die. So this is a very, very clear statement of the rules as we read them in there. Now, what I'd like to look at with this is, first off, is there any duplication in this code? What's the duplication? Number of neighbors, there's that. There's the number 3 shows around. So one way that a lot of people do is they go and they say, well, look at that number of neighbors 3, look at that 3, look at this 3 and 3. These 3s are duplicates. So we can get rid of that and do something like this. If I'm alive and number of neighbors equals 2, or if my number of neighbors is equal to 3. And then say, aha, I just shrunk the code. That must be a great refactoring. But the problem with this refactoring, which seems like a reasonable one, is that it's misunderstanding what knowledge is. It's looking at that 3 and thinking that those 2 3s are the same. It leads us to a situation where we now have 2 different pieces of our code, 2 different pieces of our rule set, the rules for when you're alive and the rules for when you're dead, and we have them mashed up together. And this makes code hard to change when you have different pieces of your system all sort of mashed together. If somebody comes and tells you, I need to change the rules for a dead cell, it makes it harder to come in. And so it's really about looking at it and understanding what the knowledge is. So if you get rid of that refactoring and start thinking in terms of what these should be named, we're mixing in a lot of code here. It's kind of a little hard to read. It's not very expressive about what the domain looks like. So you really might think about if you take a different strategy and instead focus on your names. You might say that if I'm alive, then I want to look to see am I in a stable environment. Pull that out to a method. You might also on this one say in we'll call it a genetically diverse environment. So a different refactoring is by focusing instead on the names of it and making it concise, making it clear, making it very expressive, and looking at it and saying, well, if I read this code, it says, if I'm alive in the next generation, if I'm alive, then I look to see if I'm in a stable environment, otherwise in a genetically diverse environment. Now, That's all fine and dandy, but how do you choose which one do you do? How do you choose not to take that 3? And a lot of the time, it's because we're focused on the code level. We're focused on this number. And so before you come and say, these 2 3s are the same, I'm going to sort of refactor this, take a larger look and look at a slightly larger scope. The number of neighbors equals 3, which is actually part of this statement. This statement is not the same as this statement. It's not about the code, it's about the concept in the code. It's about making it expressive and clear what you're actually doing. And that's why taking a naming approach can be very handy. So there's the first example. The second example is about looking at, so we look at this code. We want to look at it and look at it in terms of what this alive is. So if you look at this if statement, there's a little bit of a smell in that we have this if-else statement, and in general, those aren't all that great. But if we think about it, just having this alive here makes a really strong statement about what our code is intending to do. This is saying that sort of the default situation for a cell is alive. It says, I prefer it to be alive. And if I asked you, what's the other option? It's not as expressive in this. It doesn't very clearly state it's alive and dead. You're sort of assuming that those are your situations. What you also run into is the fact that if I need to add, what if I need to add a new state? What if I need to add this? So what I'm doing is I have this attribute called alive, but it's not really descriptive of the cell. What we really are looking for is something that is more along the lines of what's the state of the cell. Because it doesn't just ripple between true and false. It ripples between a concrete idea, an actual concrete state. And so we might want to look at it and think of it in terms, let me move these as I'm done. So we might take that and say, well, since alive doesn't include the other option, it's not as expressive, it doesn't include the entirety of our domain, we might change it into something like state. And at that point, you might say, aha, well, then I can do something like this. And that's a little more clear. It's a little bit more clear to look at that. I should have made this font a little bigger, too. I'm getting old with my old age. But there's a couple problems with this. One is that we're missing a default. We're still mixing up the algorithms. We're still mixing up the decisions about what do you do when you're alive and what do you do when you're dead. If we change one of those aspects, we then end up in the same code as the other one. So if we need to change something about alive, then we are in the same code that has to do with being dead. And that's a little bit of a problem because it's dangerous. It makes our code a little bit more fragile. Because if I come in and I make add new rules to being alive, and it breaks being dead, often we run into that. I mean, I know I run into it a lot where you make a change somewhere, and it breaks something that's really unrelated. And so, coming into this, we're running into something that I term, procedural polymorphism. Ooh, is that readable? I'll just write it like this. Procedural polymorphism. So if you think about polymorphism is a way to either call a method or send a message to an object and to have more than one behavior happen. I can call a method, I could do something like generation, and it's not, it could be one of two different behaviors. It could be one or two different algorithms based on this thing at the top, this alive and next generation. And so what we're doing here is we're taking a procedural technique and we're applying it in an object-based or an object-oriented language. So it's not in and of itself bad, but it does have the potential to cause problems because procedural polymorphism tends to tightly couple the different branches together. I don't know if you've heard, there's a lot of times people bring up this idea of, don't use if statements or don't use branching. And this is really what they're talking about, is being able to make your code very single purpose so that when you do change it, it's easier not to break other things. And so the technique that I tend to use is one of my favorite words in the English language, which is reification. What reification means is to take concepts and move them, elevate them into existence. Is taking a core concept in your system and making it a first-class entity in your system. And the way you do that a lot of times is look at the actual branching conditions and think about what they represent. So the state equals alive represents a living cell. State equals dead represents dead cells. And so whenever you find yourself in a situation where you have this procedural polymorphism, where you have if statements, a good way to get around it is to elevate them into types. So at this point, I then could have something like alive and next generation. In stable environment, genetically diverse environment. And so at this point, what I've done is I've taken a piece of code that has very tightly coupled two different aspects of the system, two different algorithms, and separate them into two very, very simple constructs. And you can even, if you want, if you're of that nature, since this is, number of neighbors equals 2 or number of neighbors equals 3, you could say, well, I probably could just drop it, bring that down, bring that extra method, that extra message that's being sent. I could probably drop it down for this case because it's so focused. And so it allows us to name things, pull them out into reified objects, and then simplify even further. And so at this point, I now have taken procedural polymorphism, a if statement-based branching, and moved it into type-based polymorphism. So this is now type-based polymorphism, which I will go so far as to say is the preferred form of polymorphism for object-based languages. A side benefit of this is if you study the solid principles, the single responsibility and open close and list-gov and interface segregation and dependency inversion, this one actually better satisfies what's called the open closed principle, which states that a system should be open for extension, closed for modification. This says that if you want to change your system in some way, adding new features, it's best to add code, add new structures, than it is to change existing code. Because once you have code out there and you've tested it and it's working, the worst thing that you can possibly do is to change it. Because then you have to retest it, refigure out if you've broken anything. Whereas suppose we have a third type. We have something like a zombie cell. And it has some sort of rules. At this point, I can simply add new functionality to my system via extension, via adding a new class. And so this really does come into play, and it's very, very nice to have. So that's another type of thing. It gives you a good way. The other thing to look at is it gives you the opportunity to start looking at these names a little bit better. If you look at the domain, if you look at this game of life, it talks about living cells coming to life, and it talks about dead cells coming to life and living cells staying alive. It doesn't really talk about the implementation. Alive and next generation is much more closely related to the implementation of the system, where you're going generation to generation, rather than the higher level concepts that are in your domain. So by taking these out, we can do things like, let's give it a better name. And so we continue to apply these 4 rules of simple design by looking at this conciseness and this expressiveness and saying, aha, this expresses a little bit better the system that I'm working in. So this might be, eat something, because zombies, of course, eat people. So that's the second example that I want to show, just around naming and around this idea of using procedural or converting procedural polymorphism into type-based polymorphism based on looking at the names and looking at really what these variables, these instance variables or properties mean. Okay, so let's get rid of that one. Now that we have cells, though, one of the other things about our system is that we tend to have locations. We talk about where it is on the board. And one of the things that you might want to be able to do is, say you have a class that represents not the word, but the world. Moving on in your design, you might say, well, I'm going to have this world class that represents the grid itself. And so a lot of times, I've seen a reasonable design would be setting a living cell at some place, maybe checking if there is a living cell at another location. And this seems like a reasonable thing to write. The world may be a bad name for the class, but we won't worry too much about that. So we've probably written things like this. But if you think about it, you also might come into your class, living cell, and add an X and a Y property. And say, okay, well, cells have this XY value. They know where they are on the grid. I can, from an external client, call setLiving, check whether it's alive somewhere. Now, there's a subtle duplication here that is not always picked up on. Anybody see a duplication here? They share the location, that's something. There's an even more subtle is this XY. Look at this XY. It's repeated over and over and over again. Now, if I asked you to change the topology, to change the dimensionality of your system, how many different places do you have to go in and change? 4. And you could already. And I'm only 30 seconds into typing. So you've already got this duplication. And this really goes into that idea of duplication of knowledge. It's about looking at this XY. That XY is a very concrete case of knowledge of our topology, knowledge of what the grid looks like, knowledge of where we are. And it's very easy to remove that. And you remove duplication generally by extracting things. So what you do is you take this knowledge, this concept, and maybe you make a new class called location, and it has the X and the Y. At this point, you basically are just passing locations around. So, like this. Now, if I ask you to change the dimensionality, change the topology of your system, How many places do you have to change it? Just the one. Nobody else really cares about it. And I'll repeat again, these are very subtle. These are sort of things that in your day-to-day coding you might go, well, this is just taking it to the extreme. And it might be. But how many times have you gone in and had to make a change, and it should have been a very simple change, and then find that you have to repeat it over and over? And it doesn't take that long to extract it. I don't even have fancy refactoring tools like you do in C# and Java. If you were in that, it would be even simpler to do. This again relies on this concept of taking a piece of knowledge, a concept in your system, and creating a real thing from it, creating something that you actually can see and feel. And another thing is location is such a core part of this system. We're going to have neighbors. We have to figure out where things are relative to each other. And yet, it's so easy to just go, I'm going to pass X or Y around and not make it into a core part of your system. We can also, if we wanted to, approach this problem from the concept of naming. X and Y are awful names. The fact that we know that we tend to think of them as like row and column is entirely convention. It's entirely our language. Nothing says here. So if I looked and said X, Y, which one's the column and which one's the row? You wouldn't necessarily know. You might not have to care. But just from a naming perspective, I would rather my method actually be explicit about what I'm doing. I'm setting a living cell at the location. And so you can come in here and deal with it just from a naming perspective. Now, what this would allow you to do is if you had an instance of the object, you might pass it a tuple. And what that does is by taking this and making it a location and giving it a better name, you're taking the duplication. You're taking that concept, not the duplication, but you're taking the concept that is poorly named in your method signature, and you're pushing that poor naming up your stack a little bit. And you can continue to do that up and up and up. And eventually, eventually you can probably do something and keep pushing it up. Eventually you end up saying, oh, well, I clearly need some sort of duplicate or some sort of location concept here. Okay, so this is a really important one, and because of the subtlety of this understanding that duplication and the dry principle is about knowledge in your system. It's not necessarily just about the fact that there's code. So we talked about this duplication as well, where we have both the living and the dead cells have the X and the Y in them. Now, one thing you might want to do, and unfortunately I see a lot of people doing this, is moving this up into a base class. And I'll just say one thing. For the love of all that is good and holy, stop using base classes. Stop doing inheritance. And that's a whole nother talk as to why. Instead, let's look at the solution of this from, we do have duplication here. Both of these cells contain this location. But rather than taking a very awful and God-forsaken construct like inheritance and using that as the way to solve this, instead, take it as an opportunity to go, well, maybe it isn't cells that have locations, but maybe locations have a cell. What is the cell? We already, when we built our cell in the past example, we had the cell responsible for the business rules about whether it continued on in the next generation or the previous generation. So if I have this cell with a method called stays alive, and I also have this where it has, how many different things is this doing now? It's keeping track of where it is, as well as keeping track of business rules. This tells me that the cell is sort of, what's the meaning of cell? Is it a good name for it? If it's doing both of these things, is it managing rules? Is it managing the locations? So by taking it out of there, instead of just moving it up and getting it out of the way with the base class, actually ask yourself, can I take it completely out? And by doing that, by creating a location object, you already have a place. And we created this location object based on something completely different when we were removing the duplication about our topology. And where's my little marker? Here it is. The other really nice thing about this is that oftentimes you might have one of the things that we kind of need to do is have a method. One of the things, if you looked at what we had, this is probably a method we need. Part of the game, part of the rules of the game have to do with counting the number of living neighbors. So it makes sense that you would have a method called give me the neighbors for this. Now, where does this method go? Does it go on the cell? Does it go on the world? We have our XY, so we're not yet building that. Because, though, we had extracted out this location object, because we had reified this concept into our system, we have something that I call a behavior attractor. If you start moving through and very aggressively reify concepts in your system, take those XYs, find that duplication, and move them into real parts of your system, you end up with a lot of classes that are exactly fit in your business domain. This location is a really strong aspect of the rules. It's a strong aspect. Now, it just came to life because we were eliminating some duplication. It came to life for something totally different. We were isolating that XY, the knowledge of the topology. But down the road, we end up wanting to look at what the neighbors of a location are. And when you think about where to put methods, there's generally two ways that we do it. Generally, when we make decisions about where to put things, we either go, where is it closest to my data? Or more likely, what code file do I have open right now? You laugh because it's true. I laugh because I've done that many, many times. But when you are pulling these real concepts out, very, very often you find that you already have a concept, a class that is accepting of that method. It's clear. If I came to somebody and said, look, I have this location object, I have a world object, and I have a cell object. Where should I put something that talks about neighbors of a location? The location object. So you end up with, oops, bye. You end up with these classes that when you have a new behavior, they're sort of just attracting them. They're like, come on, I'm the place to do it. And so these are what I call behavior attractors. And you see them a lot around this. You really do start to see these pop up in your system a lot. Okay. Okay. My last example. Throw these down here. 1 second. Let me pull up my clock real quick. Oh, look. Oh, thanks. I actually threw them on the ground, but I didn't throw them angrily enough. Okay, another thing about naming is I haven't talked anything about testing, and of course, you all aggressively write tests for your code, right? So one of the things is I'm going to give you an example of a test. So when you first start, you might say, well, I'd like to start at the world and talk about adding cells to the world because I need to set up my initial pattern. So you might be like, test, a new world is empty. That's a reasonable test name. So I can come in here and say, give me a new world, and then assert that my world's living cells, and let me count them, is 0. And we put the code in there, return 0. We write a new one, test. A world with a living cell is no longer empty. So we might go here, and let's say set living at, let's create a location object. I wish I had time, I would talk about why I dislike that, but we won't. And then we go on when we implement it. But when we talk about test names, we talk about how our test names really should be describing the behavior of our system and less about the low-level implementation. And I kind of did that here. I said, test a new world is empty. Test a new world with a living cell is no longer empty. That's really kind of talking about how the higher-level behavior aspect of it. We don't come in here and say, def test the count of living cells of a new world is 0. Hopefully, people wouldn't write that test name. Instead, you do this. But look at the code that's in there. There's no symmetry here. So we are saying that the world is empty, but we're actually calculating world.livingcells.count. We're not letting the test name influence our API design. One of the things we talk about with TDD is that it's a design methodology, and one of the aspects of how you can do it is by writing your test name, putting the effort into the test name to make it good and make it really descriptive of your behavior, and then we write our code to reflect that. The writing of the test name is our first sort of thought around it. And so one technique is to take your test name and actually use that to reflect it in the code itself. So we would want to maybe write, is my world empty? Our test is our first consumer of our component's API. So by being clear about our behavior and then letting the test name dictate what the API looks like, we're letting the client of our API, the client of our component, dictate what the API is going to be. And I would put forward that this, I would also put forward that I wrote this wrong. Assert false, that my world is empty. And so by really taking the test names, which we tend to put a lot of effort into thinking about, what are we describing, and having it directly reflect in the code that we're writing, we can build up nice APIs. As a side effect of this, we tend to also get sort of a bonus abiding by the law of Demeter, where we're not reaching into the world, reaching into it, grabbing out all of its living cells, and then asking if those are 0. That's a rough thing to do, and worlds don't like it when you reach into them. So really highlights that importance of taking and spending the time on the names and then letting the names dictate down to where you are. I'm out of time. That's just a couple examples of things that I wanted to share that I've seen over the years that a lot of people over and over again tend to do when they're coming up with a situation. I think that as I've looked at these, I see these a lot in my own code base. I see these a lot in other people's code bases. So, as you go back and start writing code, think about names and think about duplication, not of code level, but of behavior, and see about reifying real concepts into your system. All right, with 26 seconds left. Thank you very much.